Welcome students. In the last session we discussed about the equipotential surfaces and what is the relation between electric field and electric potential. Equipotential surfaces are definition is for 1 mark and the properties are for 3 marks, and the relation between electric field and electric potential is also an important question in the annual examination, that is also given in 3 marks. Okay. Now in this session we are going to discuss about the potential energy. Now see what is the potential energy. Here I already told you, if you take a charge and the charge is having electric field in this direction. If you want to move a small charge from infinite distance to a point in the electric field P, you have to do certain work. That work done can be called as potential energy. Now according to that I am giving the definition for potential energy. The definition for potential energy is potential energy of a charge at a point is the work done by external force. That force is equal and opposite to the electric field in bringing the charge from infinite to that point. In general words, if a charge is taking infinite distance to a point P in the electric field, we have to do a work. That work can be called as potential energy. Now this potential energy will be denoted by the term U, and the SI unit of potential energy is similar to the work done, that is nothing but joules. Okay, it is represented with J, and dimensional formula of the potential energy is similar to dimensional formula of work done, where work done is equal to force into displacement. Similarly here also we know that force ml t power minus 2 into displacement is L. Finally the dimensional formula for potential energy is ml square t power minus 2. Once again see the definition for potential energy, that is the potential energy of a charge at a point is the work done by external force, which the force is equal and opposite to the electric field in bringing the charge from infinite to that infinite distance to that point is called potential energy. The potential energy is denoted with a term U, and its SI unit can be taken as joules, and its dimensional formula can be taken as ml square t power minus 2. Okay, now we are going to deriving the potential energy for system of charges. Before that, here in this we are going to take two cases. Those two cases are when system of charges are taken in the absence of electric field. When electric field is absent means electric field should be taken as 0. Then the potential in that electric field, there is no electric field and potential can be 0 and work done can be 0. So this is an important case for exam point of view, and how to derive the electric potential energy in the absence of electric field. Here we are going to take the system of 2 charges and system of 3 charges, and another case is case 2, that is in the presence of electric field. Already electric field is there. In that electric field, if you place the charges, what is the work done we have to do? So now the potential energy for these charges can be calculated for 2 different types of systems. One is in the absence of electric field, and the other case is for in the presence of electric field. In the absence of electric field and in the presence of electric fields, we are going to take the 2 systems. That is, when system of 2 charges are taken, how to calculate the potential energy. When system of 3 charges are taken, then how to calculate the potential energy. In the similar way, the same system of charges can be taken in the presence of electric field also. Now we are going to derive, and here remember these 2 are important derivations for the examination, but in this they just ask the expression only. Here 1 mark questions they given in this concept. For 2 and 3 mark question they given this concept. Now see the potential energy in the absence of electric field, I take the first one is 2-point charge system. Means I take a system which is having only 2-point charges. That is, consider a system of charges Q1 and Q2. Now I take a region. That region is represented with XY coordinates. I take a region. This region is in the absence of, means this region does not consisting any electric field. Means here the region is having absence of the electric field. Initially in that region electric field should be 0. Now the first charge Q1 is moving from infinite distance to this region. Then a point A can be taken. First we need to move the charge Q1 from infinite distance to the point A in this region. Already in this region no charge, means no electric field. When there is no electric field, potential should be 0. When potential should be 0, the work done to move the charge Q1 from infinite distance to a region which is having 0 electric field, then required work done should be 0. So here I place the charge Q1, then work done to move charge Q1 from infinity to point A is W1, but the W1 can be taken as 0. Why? Because we move the charge Q1 from infinite distance to electric field 0 region. Due to that, work done should be taken as 0. And next one, when we place the charge Q1, due to this charge Q1, such electric field can be formed in this region. Now we have to move a charge Q2 from distance infinite to the point B. This point B is at a distance of R12 from the charge A. Now when you want to place the charge Q2 from infinite distance to that point B, then work done to move charge Q2 from infinity to B. The work done to move the charge from infinity to B can be taken as W2 is equal to Q2 into potential due to charge 1. Remember this one. Previous no electric field, so work done is 0. But now electric field is formed by Q1. Then we place the charge Q2 from infinity to that electric field region. We do certain work, and that work done can be taken as moving charge Q2 into potential due to the charge 1. That is Q2 into Q1 by 4 pi epsilon naught into R12. This is equation 2. Now the total work done, W is equal to W1 plus W2. W is nothing but 0, W1 is 0, W2 is Q1 Q2 by 4 pi epsilon naught R12. We know that work done is nothing but the potential energy. Finally, potential energy of system of two charges is nothing but Q1 Q2 by 4 pi epsilon naught R12. This is the potential energy in the absence of electric field when we consider system of 2-point charges. Again, see this derivation, how we find the potential energy of 2-point system. This is important for 2 marks. See here. First, I consider a electric field 0 region. There, electric field is absence. Now, I consider a system of charges Q1 and Q2. First, I place the charge Q1 from infinite to the electric field 0 region. Then, there is no work done is required. So, to move the charge from infinity to point A is 0 work done. The work done required is 0. Now, when you place Q1, then due to that Q1, an electric field is formed here. In that electric field, again we place a charge Q2. Now, the work done required to bring the charge Q2 from infinity to the region then we have to do certain work. That work can be taken as W2. W2 is equal to moving charge is Q2 and the potential due to the charge 1 V1. By substituting here, the work done required to move a charge Q2 from infinity to the point B is known as Q1 Q2 by 4 pi epsilon naught R1. And here we have to take total work done. The total work done is nothing but W1 plus W2. Addition of these two, we can get a total work done to bring the two charges in the absence of electric field. That is the total potential energy. Therefore, total potential energy U equal to Q1 Q2 by 4 pi epsilon naught R12. Now, previous we derived the two point charge system. Now I consider the system of three charges. Okay, here again, how to calculate the potential energy of system of three charges in the electric field. Generally this question is given for the only they are going to ask expression, but in the previous question is they given for the 2 marks. Okay, so keep practice this one. Now see the 3-point charge system. Again here I consider three charges. Consider the system of charges. Here the number of charges are 3. Those are Q1, Q2, Q3. And again I consider a region, and here it is a zero electric field, means in this region electric field is 0. Now because this derivation is for absence of electric field. So, see here, charge in the absence of electric field. In the next we derive in electric field also. Okay, now this is the potential energy of system of three charges in the absence of electric field. Okay, now I consider the three charges Q1, Q2, Q3, and here the region is having 0 electric field. Now first I need to bring a charge Q1 from infinity distance to a point A in this region. But this is 0 electric field is there, then the required work done should be 0. So due to that, work done to move charge Q1, the work done to move charge Q1 from infinity to point A is W1, but the W1 is 0. Why? Because here electric field is initially 0. And after, when the charge Q1 is placed, now this region is having the electric field due to this charge. Now work done to move charge Q2 from infinity distance to point B. I take a charge Q2 from infinity to point B, then here the distance can be taken as R12. Now a work done should be done. That work done is W2. W2 is nothing but, here the bringing charge is Q2 into potential due to the charge Q1, that is Q1 by 4 pi epsilon naught R12. Now the W2 can be taken as Q1 Q2 by 4 pi epsilon naught R12. This is equation 2. Go. Now the third charge Q3 is bringing from again infinity to the point C in that region. Already in that region we placed two charges. Now these two charges are applying potential at point C. So due to that we assume distance between A and C, or Q1 and Q2 can be taken as R13. Distance between B and C, that is between Q2 and Q3, can be taken as R23. Now the third one is work done to move charge Q3 from infinity to C is nothing but W3. W3 is equal to, on this charge the field is acting, on this charge the field is also acting, then W3 is equal to Q3 into potential due to 1 on 3 plus potential due to 2 on 3. By substituting here, this is Q3 into V13, potential due to 1 on 3 is nothing but Q1 by 4 pi epsilon naught R13 plus Q2 by 4 pi epsilon naught R23. That is the potential. Now from this we are going to, this is the work done on third charge. Therefore total work done is nothing but potential energy in the 3-point system. Therefore the total work done is potential energy. Potential energy is nothing but addition of W1 plus W2 plus W3. So from that we are going to write W1 is 0, W2 is Q1 Q2 by 4 pi epsilon naught R12 plus W3 is nothing but Q1 Q3 by 4 pi epsilon naught R13 plus Q2 Q3 by 4 pi epsilon naught R23. Now this is the total potential energy in the 3-point charge system. See here, once again I repeat this one. Here I consider 3 charges and a electric field 0 region. First I place the charge Q1 from infinity to the point A, then the required work done is 0. And again I bring the charge 2 from infinity to point B, then the work done is Q2 into potential due to charge 1. Next, if I move the charge Q3 from infinity to point C, then these two charges are providing a electric field. Then the total work done W3 is equal to Q3 into V13 plus V23. Here from that, this is the potential due to 1 on 3, this is the potential due to charge 2 on 3. From that, this is the work done to move the charge Q3 from infinity to that point. Therefore total work done is nothing but W1 plus W2 plus W3. Therefore total energy is nothing but total energy, that potential energy is equal to sum of all the work dones. It gives the Q1 Q2 by 4 pi epsilon R12 plus Q1 Q3 by 4 pi epsilon R13 plus Q2 Q3 by 4 pi epsilon naught R23. Okay, from the above two derivations, that is system of 2-point charges placed in the absence of electric field, we calculate the potential energy. And the second derivation, system of 3-point charges are placed in the absence of electric field, we derive the potential energy. By observing those two derivations, we can write the direct formula or direct equation for the, if n number of charges are present in the system, what is the total potential energy? That potential energy will be given by 1 by 4 pi epsilon naught is common, and here one charge is represented with I, other charge is represented with J, and here we take sigma I is equal to 1 to n, sigma j equal to 1 to n, qi into qj by rj minus r1, where I is not equal to 0. Why? Because in our derivations we are not observing that q1 into q2, q2 into q2, q3 into q2. That is not possible. That's why in that we are going to take I is not equal to j. So like that we are going to write the system of potential energy due to system of n-point charges can be taken. Okay, so these are the derivations for the potential energy due to system of charges. First derivation is, we take the system of charges are 2. We take another, the second derivation is the system consists 3-point charges. Now in this the system consisting the n charges. Okay, so from this we are going to calculate what is the potential energy. Remember, this is in the absence of electric field. In the next session we derive what is the electric field, what is the potential energy in the presence of electric field. There we take the total 4 simple derivations. One is single charge is placed, what is the potential energy? System of 2 charges placed, what is the potential energy? System of 3 charges are placed, what is the potential energy? And similarly, an important 3-mark derivation, if we place the dipole in the electric field, what is the potential energy due to the dipole, and what when it is max, when it is minimum, we see in the next session. Thank you.